Hello everyone, it's Mr. Wolf here, and in this video I'm going to be going over number 2 for the LT5a solving word problems with energy and work. So in this case, a car that's 100 kilograms is driving the road at 40 meters per second. So right away, even before my LOLs, I kind of like to just draw a picture to get my variables straight. So here's the car, driving on the road, and let's see, the mass is 1,000 kilograms. And it's going, so my initial velocity is 40 meters per second, let's say. And when there's it sees a sudden traffic jam, it slams on the brakes, which causes a force of 10,000 newtons and comes to a stop. All right, so it looks like my ending point, I'm at a stop. So my final velocity is 0 meters per second. It looks like, by the way, since I'm on the ground this whole time, that I could write this down. I don't have to write this down, but my height is 0 meters. Height is 0 meters just because I'm on the ground. And then it looks like we have that force of friction right here. So maybe I'm just going to draw it in the middle. Force of friction is equal to 10,000 newtons. All right, so now we got our variables down. We could use these to help us inform what's going to go on here for my LOL diagram. So as always, driving before braking is their velocity and is their height. Again, we're on the ground, so no height, which means no UG. Is there velocity? Yes, we're going at 40 meters per second, right? So if that's the case, I want to make sure that I have kinetic energy. I get to choose how many blocks. You could have 2, you could have 3. I'm going to decide to have 4 energy blocks in this case. Right. Now at the very end, right, I could, by the way, just go straight to here and say, is there energy transfer out of my system? I'm going to always ask the question, is there an outside force? Yes, there is. Right? It's this force of friction that's going to take energy out of our system. Kind of know that intuitively. So I'm going to label this as work, and I know I'm going to have, let's just say, at least 1 energy block come out, right? But what I actually have to do is I have to go to the end to figure out how many blocks exactly are coming out of this system. So just as always, when it's stopped, I'm going to ask the question, is there velocity? Is there height? I'm on the ground, so no height, which means there's no potential energy. There is no velocity because it is stopped, which means I have no kinetic energy. So if there's no mechanical energy left for my LOL diagram at the end, that means that all 4 of these blocks had to leave my system. So I still have 4 total energy units before, 4 total energy units afterwards. The only difference is that energy is no longer in my system. And when I mean system, the car. All right, so now we have our LOL. The whole purpose of this is to make our equation. And then I kind of realized I kind of marked this up right here. So there's not a whole lot of room to write my equation. So maybe I'm going to just write it maybe a little bit below here. So here I have kinetic energy. And initially, we have work, and it's leaving our system, so minus work, and that's going to be equal to 0. All right. So what I could do is I'm actually going to draw everything down here now. I could still fill in my variables, but this is why I'm going to do it here, is because if I have k minus w equals 0, I guess I could still set up my equation and fill in all the blanks, and I would eventually still get the same answer. But what I like to do is just subtract w, or get w over the other side. So what I mean by that is I'm going to add w to both sides. So now my equation, instead of being k minus w equals 0, it's just k is equal to, because the work cancels out here, is equal to 0. Or sorry, equal to work. So kinetic energy before is equal to my work that ends up coming out. Kind of makes sense right here, right? 4 here and then 4 out for work. All right, so now I'm going to expand my problem, or my equation, where k, we know the variables, or my equation for that is 1/2 mv squared, and for work it's force times distance. All right. Now, guys, I just kind of made a mistake right here where I just started kind of just going through the motions of making my LOLs, deciding my equation. I didn't even recognize the first step we should always do is, what are we solving for? And sometimes this might happen where you kind of recognize this halfway through the problem. So it says calculate the distance the car slides as it comes to a stop. So again, this is what you should always be doing first off. And I made that mistake just now. It happens. So distance is what I'm looking for. So distance equals question mark, and I can even write it here in my problem. All right. So now I know I'm solving for distance right here. I have an equation that has that variable. And let's see, 1/2. My mass in this case is 1,000 kilograms, right? My initial velocity is 40 meters per second, and then I'm going to square that value because it says so in the equation. And then my force is 10,000 newtons. And then I'm solving for my distance in this case. All right, when I do the math here, I have to, order of operations, I have to square this 40 first. So I'm going to square 40, and once I have that value, I'm going to multiply it by 1,000, and then by 1/2. And I'm going to draw this over here now, 80,000 for that number. And then that's going to be equal to 10,000 and then my distance. So I'm going to divide 10,000 by both sides, and I'm going to get my final answer to be for my distance that it took this truck 80, I guess it is a car, 80 meters to come to a stop. That is a long distance, right, for it to come to a stop there. Which, by the way, you'd be surprised how long it actually takes cars to stop when they are going at speeds like this. So my final answer is that my distance is 80 meters. Thanks for watching.